In today's episode of Nobel Prize 2020, we'll talk about the Nobel Prize in Physics. On the 6th of October 2020, 3 laureates shared this year's Nobel Prize for their discoveries about one of the most exotic phenomena in the universe, the black hole. Roger Penrose showed that the general theory of relativity leads to the formation of black holes. Reinhard Genzel and Andrea Ghez discovered that an invisible and extremely heavy object governs the orbits of stars at the center of our galaxy. A supermassive black hole is the only currently known explanation. Black holes are regions that contain so much matter packed within so little space that gravity has a runaway effect. The matter collapses toward a central point of immense density, called a singularity. Everything within a certain distance of the singularity becomes gravitationally trapped, destined to fall inward. Even light that passes inside the black hole's spherical surface of no return, called the event horizon, gets sucked in, which makes black holes invisible. A common way to visualize a black hole is as a two-dimensional sheet stretched into a funnel. Albert Einstein's general theory of relativity predicts that the curvature of space-time becomes infinite in a black hole singularity. Black holes form when matter or energy is packed together densely enough. When stars at least 10 times more massive than the Sun run out of fuel. With outward radiation pressure no longer able to counteract the inward lurch of gravity, the star's core inwardly collapses, an event usually accompanied by a dramatic explosion called a supernova. To form a black hole, Earth would have to shrink into a sphere smaller than a ping-pong ball. Researchers had tied themselves in knots trying to figure out whether objects like the Schwarzschild solution of Einstein's equations, the simplest kind of black hole, worked out on paper by Carl Schwarzschild in 1916, were really possible in nature. Such theoretical solutions had only been studied under the simplifying assumption that the material doing the gravitational collapsing is a perfect sphere. The question was whether the resulting singularity was simply an artifact of that perfect spherical symmetry, something possible on paper, but preposterous in nature. Roger Penrose made his key contribution in 1965 in his paper and showed that deviations from spherical symmetry cannot prevent space-time singularities from arising. In other words, even when a star is distorted, it will still collapse down to a point. He showed this by introducing the notion of a trapped surface, as well as a now famous diagrammatic SCHM for analyzing how the surface sits inside space-time. Unlike a regular surface, which can have light rays shooting away from it in any direction, a trapped surface is a closed two-dimensional surface that only allows light rays to go one way, toward the center point. Penrose found that the dimensions of space and time switch roles inside a trapped surface. Time is the direction pointing toward the center, so that escaping a black hole is as impossible as going back in time. Penrose, together with Stephen Hawking, soon showed that a similar analysis applies to the entire universe. A singularity would have inevitably existed when matter and energy were densely packed together in the Big Bang. Reinhard, Genzel and Andrea Ghez each lead a group of astronomers that, since the early 1990s, they tracked the motions of stars that swing very close by. If Sagittarius A was an extended cluster of material, then stars passing through would be pulled on from multiple directions, and their resulting orbits would be unremarkable. But if it was a compact supermassive black hole, then the stars should whip by at high speeds. The measurements of these two groups agree, with both finding an extremely heavy, invisible object that pulls on the jumble of stars, causing them to rush around at dizzying speeds. Around 4 million solar masses are packed together in a region no larger than our solar system. Using the world's largest telescopes, Genzel and Ghez developed methods to see through the huge clouds of interstellar gas and dust to the center of the Milky Way. Stretching the limits of technology, they refined new techniques to compensate for distortions caused by the Earth's atmosphere, building unique instruments and committing themselves to long-term research. Their pioneering work has given us the most convincing evidence yet of a supermassive black hole at the center of the Milky Way. The discoveries of this year's laureates have broken new ground in the study of compact and supermassive objects. But these exotic objects still pose many questions that beg for answers and motivate future research.